Hello everyone, and welcome to this presentation on the effect of moisture condition on the microstructure and design of concrete with recycled concrete aggregates. I'm Alexander Brand from Virginia Tech, and I'll be talking today about some of the work that we've been doing on assessing how the moisture condition of these aggregates really can dramatically impact the microstructure and perhaps how we may consider design considerations accordingly. So what is recycled concrete aggregate, or RCA, as it will be defined throughout this presentation? Some people may have different definitions. In my view, I will call RCA basically a cleaned version of construction demolition waste, right? So construction demolition waste can contain a lot of additional materials such as, brick, mortar, tile, glass, in addition to concrete, right? So when it's a stockpile of all these mixed materials, we may consider that CDW, construction demolition waste, or in my view, right, a cleaned version of that where we're only looking at concrete. That, for my purposes in this presentation, will be what RCA is. So pretty much your aggregates now, again, for this presentation, are only concrete. There are no sort of deleterious or additional materials in that stockpile. Right, so of course here's just some images of an RCA stockpile. Right on the right, you'll see a lot of the steel. Right, so as you're crushing the concrete, there'll usually be a magnetic separator to pull out the steel, just in additional ways to sort of clean up that material and only pull out the concrete. So in the U.S., the government doesn't necessarily keep track of pure RCA, but they do have the history of CDW in the U.S. This is through the EPA, the Environmental Protection Agency of the U.S. government. So you can see in 2018, roughly 24% of all CDW was landfilled. These are sort of the latest statistics, but 76% was used in other applications, right? Predominantly in aggregates, right? Now, of course, here we're talking about CDW. In the case of the EPA, how they'll define CDW is basically the demolition and consolidation of steel, wood, drywall, brick, asphalt shingles, concrete, and asphalt pavement. So that's sort of all of it combined here. So again, concrete is just one part of this. Now, some of the numbers that you can find just for concrete in the U.S., it's about 140 million tons. And this is now what's recycled, right? So we're not really even keeping track here of what has been landfilled. So we don't necessarily have those numbers. But you can see here, each year an estimated 140 million tons of concrete does get recycled. The vast majority of it does get used as aggregate base. You can see where we have very little other use, right? Only 6% of that is used as an aggregate in concrete. It's a fairly low number. I would like to see that number go up, of course. Then, of course, you're also seeing it as an aggregate in asphalt concrete as well, in addition to fill and riprap. So RCA, I would say, is under some consideration in parts of the U.S. Is it important everywhere? Probably not necessarily. But certain regions of the U.S. Have a significant issue with access to quality aggregates. So this is an image from the USGS, the U.S. Geological Survey. And these highlighted areas on the map of the contiguous U.S. are areas where high quality aggregates are not as readily available, right? So there may be perhaps a lower quality or deleterious aggregate, marginal aggregate, maybe it's highly porous, right? So some other issue. So the question in those regions is, what do you do, right? How do you accommodate the need for high quality aggregates for whatever application that is, whether that's bases, aggregate and concrete, aggregate and asphalt. So of course one option is to ship it in from other regions, which of course starts to become fairly prohibitively expensive. So perhaps it's a bigger consideration of um, reusing more of what we do have readily available, and that would be things like recycled aggregates, right? So of course this is a problem that is not limited to just the United States. You'll find this in a number of countries around the world where high quality aggregate is a premium. Particularly sand is becoming quite an issue in certain parts of the world, but it's the same with coarse aggregates as well. Okay, now a number of reports from the American Society of Civil Engineers (ASCE) does publish the report card for the American infrastructure. You can find that online. And basically, what that report card shows is the U.S. has an aging infrastructure that requires significant repair and rehabilitation, something like trillions of dollars of investment to uh, get a report of an A, right, in the U.S. for the infrastructure. And the numbers for aggregates to meet that goal, right, to invest and rehabilitate and repair all of America's infrastructure, we need a 70% increase in area production to do that, right? So again, therein lies the problem where if you look at this map and you see that there are regions where quality aggregates are not necessarily readily available, if we need 70% more aggregates in those regions, again, what is there to be done? All right, so the remainder of this presentation will pretty much consider recycled concrete for that application. My research group does look into a number of different recycled aggregates as well, but for our purposes today, we'll just be talking about RCA. So here we have a nice micrograph of a virgin aggregate that's either a limestone or a dolomite, compared to an aggregate from recycled concrete. Right, and if we put on the laser pointer here, there we go. So of course you can see this limestone or this dolomite is fairly homogeneous, right? Of course there's some pores, there's some grains. Contrast that now to the RCA, very different, right? We'll see, of course, pieces of aggregate. So here we have maybe part of a coarse aggregate. Maybe these were fine aggregates, right? And then of course you'll see all of this adhered mortar as well. Right, and we'll see that in the next slide as well. Here's another fairly nice one, right, where we have, again, part of an aggregate, right? Maybe this was a larger coarse aggregate that during the crushing process broke off, right? Or maybe this was all adhered mortar here beforehand. It's kind of impossible to know at this point. But of course, you'll also see pores. So it looks like this concrete was air entrained, which would make sense from where this RCA was sourced from. They use air entrainment quite frequently. But of course, you'll also see cracking, right? So is that cracking existent from the original concrete? Is it there due to the crushing process, or is there some other issue at play? But again, what you want to see here is just there is this residual adhered mortar on the RCA, which you will commonly hear referred to throughout this presentation. So why should we be considering using RCA in this case as a concrete aggregate, right? So kind of what we've been talking about there is some question of material availability. Again, high quality aggregates are not readily available all over the US or even all over the world. Also the question of sustainability, right? As you do move to more urban environments, as you produce more construction demolition waste, what to do with that material, right? So of course you couldn't just landfill it, but that's not always economically viable, and there's not always land space to do that, right? There's also questions of economics and cost, right? Again, if we're thinking of an urban area, maybe it's a lot more expensive to ship that material out of a city to landfill it somewhere, right? Or maybe just in general, it's cheaper to use RCA than, let's say, shipping in a high quality aggregate from another region. Performance is going to be the question here. We're going to be talking about that in this presentation a bit. You will have studies that show that RCA can meet equivalent performance to virgin or natural aggregates. Other studies may not show that, right? So this is going to be sort of a question we'll talk about a little bit in this presentation. All right. One of the driving factors as to why we may or may not have equivalent performance to natural aggregates is the material variability. All right. If you already just want to consider the vast array of different formulations of concrete that can be used, even in the same region, right? So comparing the concrete we would produce for a sidewalk versus a pavement versus a high performance bridge deck next to the seawater, right? All completely different formulations, different design lives, different risks of damage, right, and deleterious performance, durability concerns, right? So, when you're collecting RCA, unless you know where it came from and what the condition of that parent concrete was, you may not necessarily know if it has chlorides in it, for instance, which could be a concern for corrosion, of course, right? Or maybe it was a concrete damaged by alkali silica reaction, right? Has that reaction stopped, or is that going to continue? And how would that affect your new concrete? So, lots of variability here we have to think about, right? So kind of for our purposes today, we're going to be assuming that the aggregate that we're using, well, at least in the studies that I'll be showing here, were all, let's say, higher quality RCA, right? We knew where the material came from. It wasn't necessarily damaged, didn't have any durability concerns. We'll talk about that in a few minutes here, right? So again, risk of contamination, we've kind of already talked about that. We don't necessarily know what the long-term performance of concrete with RCA will be, right? And some of that has to do with the material availability, right? So of course there are plenty of existing structures, that have been around for decades that have successfully used RCA and are still performing, right? But that's not necessarily guaranteed in the long term. Okay, particularly if we have a highly variable material, right? Again, if it's damaged or contaminated, these are all concerns for what the long-term performance would be. Contrast that to natural aggregate concrete, right? That we've been using for decades and decades, right? So if you have a concrete producer who has been producing the exact same concrete mix for the past 30 years and never had a problem, right? It's a question of why change it, right? If we know this is a successful mix with this natural aggregate, now we change up that aggregate. It's now a question of will that long-term performance be guaranteed? Another big concern here is it may not be allowed, right? So there could still be regulatory issues, and this is a problem in certain states in the U.S. and probably certain countries around the world as well. That RCA may not be allowed to be used in certain applications, right? Some of that has to do with some of these questions of variability and performance. But that is something to always be considered as well, is if you can actually even use the RCA for a given project. And then, of course, as I already said, with an advantage, right, RCA can have equivalent performance to natural aggregate concrete, but of course a number of studies have also shown that it may not, right? So how do you plan for that, right? So just look at some of the variability here. This was a nice review article. You can see the reference there on the side that looked at quite a number of references in the literature and basically plotted the properties of various coarse RCAs reported in the literature. And then you can see that they tried to fit some normal distributions to this. So if we already just look at this variability, let's just look at water absorption there in the bottom left-hand corner, right? Ranging from maybe something like 0.5% all the way up to 10% water absorption. That's a fairly large distribution, right? Same thing with the density. If you look at the density for the oven dry, all right, in the top left, ranging from 2,000 to almost 2,700 kilograms per cubic meter. Right? Again, some of this variability has to do with just the grade of that concrete and the formulation of the concrete, the age of it. Is it damaged? Does it have micro cracking? Right? All of these things will affect that performance. Also, things like percent of aggregate versus adhered mortar in a given RCA particle. Right? There can be quite a bit of variability here. And in that same study, they showed that some things can have a correlation, right? So sort of the lower the density of the RCA, perhaps the higher porosity it is, the greater water absorption it can be. All right, so that's what you can see as you move left along the x-axis, right? We move vertically along the y-axis. So lower density RCA tends to correlate with higher absorption. Again, probably mostly has to do with things like porosity, right? But still, there's quite a bit of scatter here, right? So you can't necessarily use one metric to predict the other. All right. Here's another study that was useful. I just put this in here just to show you the range of some of these values. That this was a study where they tried to use machine learning to predict mechanical properties of concrete with RCA. Right, so I'm not going to get into that study at all. I just wanted to show this slide, this table from that study. Right, so they collected 607 unique data sets from a total of 87 publications. Right, and if we just look at some of these line items, whoops, laser pointer. There we go. Right, so if we just look at the density of the RCA, right, kind of very similar variability that we saw in that previous study 2 slides ago. But water absorption is a much larger variability than what we saw in the previous slide. Here, the previous slide was something like 0.5 up to 10. Here they're showing up to 12.7. In my research, we've definitely found RCAs with moisture absorption or water absorption capacities as high as 12%, which is fairly staggeringly high. Right. Well, then of course, now they're looking at different mixture proportions, but I want to also show the bottom here, right? Compressive strength. So this again is just the range of the data from this total set of 607 data sets, right? And so you can see that they found research for compressive strength ranging from 6 MPa all the way to 104 MPa. Right. All right. Again, that's a fairly staggeringly large distribution, right? And so the question is, right, is all of that variability just due to, or sorry, is that range in strength only due to the mixture proportioning, or what role does the properties of the RCA play into that? All right. Those are just some things to note here. So really what I want to focus on today, and what the main focus of most of our work has been, is looking at the moisture condition of the RCA and understanding how that affects the microstructure and the properties of your concrete. Okay, so again, the moisture absorption capacity can be as high as 10%. That previous slide up to 12.7%. We've done studies up to 12%, right? These are dramatically higher than natural course aggregates, which tend to be right around less than 2%. Again, there's of course different variability just due to lithology of the aggregate, right? But granites can be maybe as low as 0.5% absorption. You might have some porous limestones that will be much higher. Right. So, of course, there is variability in natural aggregates as well, but it appears to be not nearly as dramatic as the variability in RCA. Okay. So just to go through some definitions here for these different moisture conditions, as we'll be discussing in this presentation. All right, so this is just a classic textbook definition of these moisture states. All right, so if you have an aggregate, right, your given aggregate will have surface pores, it will have interior pores, right, it will have surface texture, right. you will have these surface pores that are permeable on the surface, right? So if we have a completely dry aggregate, I'm going to be calling that oven dry through the rest of the presentation, right? So if you put your aggregate in the oven at 105 Celsius for probably more than 24 hours, dry out all that moisture, you have no water in any of these permeable surface voids or pores, right? Interior pores, right? We're going to assume those are impermeable, right? For at least the time frames that we're looking at for the surface absorption, right? So as those surface pores start to absorb moisture, right, we can have some condition where that pore is partially saturated but not fully saturated, such that if it is just sitting in the ambient environment, it may just absorb some moisture from the atmosphere, right? We can call that air dry. We then have a condition called saturated surface dry. That is where the pores are fully saturated, but the surface of the aggregate is not saturated. So there's just enough moisture in that aggregate to fill those voids, to fill those pores, and the aggregate is not going to absorb any more water into those pores. Right, and then of course, if it's oversaturated, now you have some water adsorbed to the surface, maybe as a fairly thick film. For our purposes, for the next number of slides, we're going to be looking at this saturated surface dry condition, this oven dry condition, and then another condition in between that, for our purposes, is roughly 80% of the SSD condition, right? So roughly 80% of these surface pores are saturated or filled with water. Okay. So why are we talking about this? Why is this important, right? It relates back to that absorption capacity, right? If that absorption capacity can go as high as 10%, how is that going to affect our performance if the aggregate is in one of these different conditions, right? So, let's think about an RCA that can absorb 10% of its weight in water. How is it going to affect the concrete if you add it in, if it's completely dry, so oven dry, versus saturated surface dry? And that's really something that we're going to be looking at here. So one thing to think about along those lines is something known as the effective water cement ratio, right? So of course we have a design water cement ratio, right, where we account for the moisture that the aggregate will absorb. Okay, so if our aggregate is at pure SSD condition, it is not absorbing any more water from the fresh concrete, right? And it's probably not giving any water as well. Okay, so we're not adjusting our mixing water when we have SSD. But if we have an oven dry condition, we are going to adjust the mixing water to add additional water, knowing that the RCA at oven dry is going to absorb X% of water from the fresh concrete. However, this process can be slow. All right, so here's just one example from one study where Butler looked at an RCA that had a 7.8% absorption capacity, and that took 8 hours to reach full saturation, or SSD, right? So what you should consider here, right, is if we do have an oven dry RCA, and let's assume it's going to absorb, let's say, 10% of water, so we add additional mixing water as we're mixing the concrete, as we're batching the concrete, that additional mixing water is not immediately getting absorbed by the RCA, not by any means, right? If it's taking multiple hours to reach full saturation, and our setting time is perhaps only a few hours, we may now have a problem. Okay, so we discussed this known as the effective water cement ratio, because now it's going to be different than the design water cement ratio, at least locally, right? So that oven dry aggregate is not uniformly pulling in water from the entire mix, right? You still have to wait for the water to sort of diffuse through. So locally, around your RCA is now where you're going to have a different water cement ratio. All right, so now we have the risk of possibly having a gradient, let's say, of water cement ratio as a function of distance from that RCA. Okay, and how is this going to affect our properties, right, and microstructure? And this is exactly what we're going to be talking about in the coming slides. So this is just another important consideration from another study. And this is a nice showcase of how these different moisture conditions will affect just your workability. Okay, so here's a study where, in this case, I'm showing the data for the mix with 100% RCA, coarse RCA. They blended two different RCAs. The absorption capacity was around 6 to 7.6%, and they looked at an air dry, oven dry, and SSD condition. And so what you should note here, right, is that the oven dry for freshly mixed concrete, oven dry had the highest slump, which is no surprise because we've added that additional mixing water, right? So our effective water cement ratio now is high, so no surprise we have a higher slump. But of course, as that oven dry aggregate starts absorbing more and more water, you can see that we start to lose slump fairly quickly, right? So oven dry has the fastest slump loss, but the highest initial slump, right? And that can become a big issue if, let's say, you have a long haul to your construction site, right? These are things that you should probably may need to consider.